Imagine a place so vast, so precise, and so cutting edge that it feels like stepping into the future. A place where raw materials, simple powders, and metals are transformed into the beating heart of electric vehicles. Welcome to the world of battery megafactories, where scale meets innovation to power our shift toward cleaner energy. But how does a bag of powder become a powerhouse for a Tesla or a Porsche? The raw ingredients. Every battery has two heroes, the anode the negative side and the cathode the positive side. Think of them like the yin and yang of energy storage. Building these electrodes is the first big challenge, and it's messy, precise, and surprisingly artistic. It all starts with a recipe. Picture a baker combining flour, sugar, and eggs, except here, the ingredients are lithium, graphite, nickel, and cobalt. These powders are mixed with a liquid solvent and a sticky binder to create a gooey paste called slurry. The slurry's consistency determines how well energy flows in the battery. The slurry's consistency is a critical factor in battery performance, and achieving the perfect balance is both a science and an art. The viscosity of the slurry must be meticulously controlled to ensure it adheres uniformly to the metal foils. Too thick, and the coating will be uneven, leading to hot spots and reduced efficiency. Too runny, and the slurry won't bond properly, causing delamination over time. Engineers often use rheometers, precision instruments that measure flow and deformation to fine-tune the slurry's properties. This step is so crucial that some factories employ machine learning algorithms to predict and adjust the slurry's composition in real time, ensuring consistency across thousands of batches. The mixing process itself is a marvel of engineering. In some gigafactories, the mixers are equipped with advanced sensors that monitor temperature, humidity, and even the chemical composition of the slurry. These sensors feed data into a central system that can make micro adjustments on the fly, such as adding more solvent or adjusting the mixer's speed. This level of automation not only improves quality, but also reduces waste, as any deviations from the ideal recipe are caught and corrected before they can affect the final product. Too thick, and it won't stick to the metal sheets. Too runny, and it'll drip off. Some gigafactories use giant mixers that look like industrial blenders. Others use futuristic, continuous mixers that work like conveyor belts, dosing ingredients with robot-like precision. Next, the slurry is slathered onto ultra-thin metal foils, copper for the anode, aluminum for the cathode. These foils are thinner than a human hair seriously, 0.14 microns thick and unspooled, like gigantic rolls of tinfoil. Even a speck of dust can ruin the coating. The clean room environment where the coating takes place is a testament to the precision required in battery manufacturing. These rooms are classified by their level of cleanliness, often meeting ISO Class 8 standards or higher, meaning there are fewer than 100,000 particles per cubic meter of air. To put that into perspective, a typical office environment might have millions of particles in the same volume. Workers entering these areas must undergo rigorous gowning procedures, including wearing full-body suits, gloves, masks, and hairnets. Some facilities even use air showers to blow off any remaining particles before workers enter the clean room. The air inside is filtered through high-efficiency particulate air, HEPA, filters, which capture 99.97% of particles as small as 0.3 microns. For context, a human hair is about 70 microns thick. The air pressure in the clean room is also carefully controlled to ensure that contaminants from adjacent areas don't seep in. This level of environmental control is essential because even a single particle of dust can create a defect in the coating, leading to a weak spot in the battery that could fail under stress. So workers suit up in clean room gear, and the air is filtered cleaner than a hospital ICU. After coating, the sheets pass through an 80-meter-long oven that's longer than a Boeing 747 to evaporate the solvent. Too much heat? The coating cracks. Too little? It stays sticky. The coated sheets are squeezed between two giant rollers to compress the slurry into a smooth, even layer. This step ensures the battery can store maximum energy without bulges or thin spots. Too much pressure can crush the material. Too little can leave air gaps. Finally, the giant rolls are cut into smaller strips, like slicing a massive cake into individual servings. The cutting process is another area where precision is paramount. For anode and cathode sheets, the edges must be perfectly straight to ensure proper alignment during cell assembly. any jagged edges or burrs can cause misalignment, which can lead to short circuits or reduced performance. Some factories use diamond-tipped blades for cutting, as they offer unparalleled sharpness and durability. Others have adopted laser cutting, which provides a contactless method that eliminates the risk of mechanical wear and tear. Laser cutting also allows for more intricate designs, such as creating tabs or notches in the electrodes that are essential for connecting them to the battery terminals. These tabs must be precisely positioned to ensure a strong electrical connection, and even a fraction of a millimeter's deviation can compromise the battery's performance. Advanced vision systems are often used to inspect the cuts in real time, ensuring that each strip meets the exact specifications required. These strips will become the anode and cathode fingers inside the battery. Some factories use razor-sharp blades, others use lasers for pixel-perfect cuts. Lasers are pricier, but avoid metal shavings that could cause short circuits. Phase 2. Cell assembly. Now comes the dry room, a climate-controlled zone so arid it makes the Sahara feel humid. Why? Moisture is the enemy here. Even a drop of water can turn a battery into a dud. Therefore, electrodes go through a drying process that reduces the remaining moisture and are transported to a climatically controlled environment that ensures the quality of the cells. This environment is called a dry room. The dry room is one of the most energy-intensive parts of the battery manufacturing process. Maintaining a dew point of minus 40 degrees Celsius requires powerful dehumidifiers and refrigeration systems that consume vast amounts of electricity. Some factories are exploring innovative ways to reduce this energy consumption, such as using heat exchangers to recycle the cold air or integrating renewable energy sources like solar panels. The dry room's climate is so extreme that even the materials used to construct the room must be carefully chosen. Standard metals can corrode, and plastics can become brittle at such low humidity levels. Specialized materials, such as stainless steel and certain polymers, are used to ensure the room's integrity. Additionally, the room's walls and floors are often coated with antimicrobial treatments to prevent the growth of mold or bacteria, which could introduce contaminants. Such rooms are generally maintained at a dew point of negative 40 degrees Celsius, although lower temperatures are required for more moisture-sensitive chemistries such as NMC 811 or lithium metal. At this stage, electrodes are cut and assembled into their cases. Although this process varies according to the cell format, like pouch, prismatic, cylindrical, there are three main activities in this block. For pouch cells, the next step is the cutting process that converts the coated rolls into individual electrode sheets. The cutting machine, which is still different for anode or cathode production, unrolls the foil and produces rectangular electrodes with an uncoated area left. This area will be the tabs required later in the assembly. The cutting process can be performed with two types of technologies: mechanical cutting, formed by a die with blades, and laser cutting. Although the mechanical system usually reduces the cost, it requires regular sharpening and replacement of the blades. On the other hand, the laser avoids direct contact with the electrodes and offers more flexibility. Once the individual sheets are produced, they go through a stacking process, which is usually the trickiest and often a bottleneck in cell assembly. This is the first stage in which the cathode and anode lines are combined. The goal is to alternately stack anode layers, the separator, and cathode layers, while leaving the uncoated tabs exposed. The most common methodology for this is Z-stacking, where the separator is folded over each electrode layer in a zigzag movement. The alignment is key in this process, as misalignment can cause the electrodes to extend beyond the separator, creating a short circuit once the cell is completed. The stacking process is a delicate dance of precision and speed. In some factories, robotic arms equipped with advanced vision systems handle the stacking. These robots use cameras and sensors to ensure each layer is perfectly aligned before placing it onto the stack. The separator, a thin polymer film that prevents the anode and cathode from touching, must be positioned with micron-level accuracy. Any wrinkles or folds in the separator can create gaps where the electrodes might come into contact, leading to a short circuit. To further enhance accuracy, some factories use automated optical inspection (AOI) systems that scan each layer as it's added to the stack. These systems can detect even the slightest misalignment or defect and alert operators to make corrections before the stack is completed. In high-volume production lines, this level of automation is essential to maintain both quality and throughput. Another alternative is stacking through lamination. This method, similar to single sheet stacking, joins two of the components together, and these are later stacked in between cathode layers in an alternating manner. Once stacking is complete, the exposed electrode tabs must be attached to the main terminals through a welding process. The cell is then placed into a preformed packing material and sealed, leaving an open edge for the electrolyte filling. Once vacuum sealing the remaining edge, the product is left to soak for hours prior to forming, aging, and test phase. The soaking process, also known as electrolyte wetting, is a critical step that ensures the electrolyte fully permeates the electrode layers. This can take anywhere from a few hours to several days, depending on the battery's design and the type of electrolyte used. During this time, the battery is often subjected to gentle vibrations or pressure cycles to help the electrolyte penetrate deeper into the stack. Once the soaking is complete, the battery undergoes a forming process where it's charged for the first time. This step activates the chemical reactions within the battery and forms a solid electrolyte interface layer on the anode. The SEI layer is essential for the battery's long-term stability as it prevents further reactions between the electrolyte and the anode. However, forming is a delicate process that must be carefully controlled. Too much current can damage the SEI layer, while too little can result in an incomplete formation. For pouch-style batteries, think slim, flexible iPhone batteries. The stack is slid into a foil wrapper, vacuum sealed, and injected with electrolyte, a liquid that lets ions zip between the anode and cathode. Phase 3. Testing. Not all batteries are created equal. Some are duds, others are diamonds. This phase sorts the heroes from the zeros. The battery is charged for the first time, waking up its chemical reactions. This step is slow and delicate. Batteries sit on shelves for days or weeks, like fine wine aging in a cellar. Engineers monitor them for voltage drops or swelling. A puffy battery is a bad battery. Then they are baked at 140 degrees Fahrenheit, frozen at negative 40 degrees Fahrenheit, punctured with nails, and crushed under weights. If they catch fire or leak, they're tossed. The testing phase is where the battery's metal is truly put to the test. In addition to extreme temperature and puncture tests, batteries are subjected to vibration tests that simulate the rigors of driving on rough roads. They're also tested for cycle life, which involves charging and discharging the battery thousands of times to see how it holds up over time. Some factories even use accelerated aging tests, where batteries are exposed to high temperatures and voltages to simulate years of use in just a few weeks. Data from these tests is meticulously analyzed to identify any patterns or trends that could indicate a potential issue. For example, if a batch of batteries consistently fails the puncture test, engineers might investigate whether there's a problem with the separator material or the stacking process. This data-driven approach allows factories to continuously improve their processes and produce batteries that are safer, more reliable, and longer lasting. But why do they do such extreme testing? Your phone battery shouldn't explode in your pocket. Same rules apply to car batteries, just scaled up. The secret sauce: gigafactories are like tech playgrounds. Robots zip around. AI predicts machine failures, and cameras scan for defects faster than the human eye. Algorithms analyze mountains of data to tweak recipes. Maybe a pinch more nickel boosts range, or less cobalt cuts costs. AI spots waste hotspots, like slurry dripping off a conveyor belt, and suggests fixes. One factory reduced material waste by 15% this way. Gigafactories aren't perfect. Mining lithium ravages deserts. Cobalt mining in Congo often exploits workers, but change is brewing. Old batteries are stripped for parts. Up to 95% of materials can be reused. Tesla's Nevada Gigafactory runs on solar power, and BMW uses blockchain to track ethical cobalt. New tech uses cheap, abundant salt instead of lithium. Sodium-ion batteries are one of the most promising alternatives to lithium-ion technology. Sodium is far more abundant than lithium, making it a more sustainable and cost-effective option. While sodium-ion batteries currently have lower energy density compared to their lithium-ion counterparts, they are ideal for applications where weight and size are less critical, such as grid storage or stationary power systems. Researchers are also exploring other chemistries, such as solid-state batteries, which replace the liquid electrolyte with a solid material. Solid-state batteries offer several advantages, including higher energy density, faster charging times, and improved safety. However, they are still in the early stages of development and face challenges such as high manufacturing costs and limited scalability. Less energy, but perfect for budget EVs or home storage. Located just outside Reno, this facility is one of the largest buildings in the world, spanning over 5.3 million square feet. That's about 100 football fields. And it's not just big, it's smart, sustainable, and packed with cutting-edge tech. The Nevada Gigafactory is where Tesla builds the batteries that power its cars, like the Model 3 and Model Y. But it's not just about cars. This factory also produces the Powerwall and Powerpack, Tesla's home and grid energy storage systems. In short, it's the beating heart of Tesla's mission to accelerate the world's transition to sustainable energy. Tesla has even announced that its Shanghai energy storage battery megafactory will start official operation this year. The construction of this megafactory in East China was completed at the end of last year. Following its launch ceremony in May 2024, it took just 7 months for the project to be completed. The megafactory is the first of its kind to be built by Tesla outside the United States and is dedicated to manufacturing megapacks, Tesla's energy storage batteries. Mass production at the Shanghai facility is expected to fully commence in the first quarter of 2025. This megafactory was built with an initial annual production capacity of 10,000 units, equal to around 40 gigawatt hours of energy storage, according to the company. For context, 40 gigawatt hours is approximately $26 billion in revenue. This could potentially be fully ramped by the end of next year, combined with Lathrop. That's about $50 billion in revenue. What's next? The future is wild. CATL, the world's biggest battery maker, is testing cells dense enough to power airplanes. Imagine a 10-seater electric plane buzzing silently from New York to Boston. No jet fuel, no emissions. These replace flammable liquid electrolytes with rock-solid materials. Safer, lighter, and twice as powerful. Toyota promises them by 2027. In China, drivers pull into stations and swap dead batteries for fresh ones in 1 minute. No charging, no waiting. While electric vehicles are the star of the show, megafactories are also innovating for a bigger energy revolution. Take home storage systems, like the Tesla Powerwall. Many use the same cells as EVs, bundled into sleek cabinets that store solar energy. On a larger scale, factories produce megapacks, shipping container-sized batteries that stabilize power grids and replace fossil fuel peaker plants. But the real jaw-droppers are the prototypes. In R&D labs, engineers are testing sodium-ion batteries cheaper, but less powerful and ultra-dense cells that could one day power electric planes. But behind all the robots are people, thousands of them. Engineers tweak algorithms, technicians fix conveyor belts, safety crews scan for leaks. That is because even a one small flaw could ruin a $100,000 car. So next time you see an electric car silently gliding down the road, remember, its power began as a bag of powder in a factory that's half laboratory, half superhero origin story. And that's a story worth telling. What do you think about this? Let us know in the comments section below, and make sure to like the video and subscribe to the channel. Thanks for watching.